Hello to everyone. This will be a brief presentation about metrology for metal additive manufacturing. My name is Leandro Vaudagna. I'm an electromechanical engineer and I'm currently doing a PhD on quality and innovation at INTI, that is an institute confirmed by INTI and the San Martin University. I've been working for almost 20 years at INTI, which is the National Metrology Institute of Argentine. And now I'm researching about 3D metal printing from a metrologic point of view. So I will talk a little bit about that and I'll mention some challenges I think we have to deal with in the near future. This is our printer. It's an EOS M290, which is a powder bed fusion type and works with the selective laser melting principle. It has some benefits like multiplicity of materials and the low layer thickness that allows really complex geometries with a good surface finish. Here you can see some technical data, but if you want more detail, you can find the datasheet on the EOS webpage, of course. On the right, there are some parts printed for training and test purpose. INTI has more than 60 years doing metrology at the highest level. It is not my intention to introduce the whole institute right now, but we can say that metrology is not a new issue for us. Although metrology for additive manufacturing, in particular on metal parts, is another thing. Talking about geometric and dimensional control, we have a size CMM, an industrial computed tomograph, and a couple of roughness meters. One of them is portable and the other is for laboratory. An important complication on additive manufacturing is the fact that the geometry and the material is made at the same time during the printing process. The material on the part is not the same as the material on the dust. And also we have to check the absence of defects like pores, cracks, and non-metallic inclusions. So we have to perform a set of tests on the final part or even on a witness specimen, which is less desirable, of course. To do that, we have the typical mechanical laboratory. We can mention a universal test machine, some durimeters, microscope, scales, microscales, and so on. Even we have an oven for heat treatment. Now, I would like to mention some characteristics of the measurement and control for 3D printed parts. 3D printing allows a high optimization of the geometries and we will have to carry out functional verifications. We will see that real-time measurements in 3D printing is as necessary as challenging. And a very interesting use of 3D printing is the production of small parts, and those require not only measurement but also calibration. There are some new design tools such as topological optimization or generative design that change the concept of dimensional and geometric controls. In this figure, you can see a real part designed and printed from a finite element simulation analysis. We can measure that and even run an actual versus cut calibration, but is that the best way to assure that the part has the expected performance? Maybe as metrologists, we will have to develop new ideas in order to define whether or not a part fulfills the desired purpose. Probably the reference for an optimized part will not be the geometry, but the expected performance. Designers, metrologists, and printer operators will have to be highly communicated and share common knowledge. Most of printed parts are unique, so it is impossible to apply statistic control or traditional validation processes. In addition, most of them are of very high value. It is highly desirable to be successful on the first try. There is a lot of research driven by printer manufacturers to do that. Sellers offers equipment measurement system and calibration as a single package. What will be the role of NMIs in that context? How will we spread traceability? How we will get the required knowledge for that? Those are some of the questions we will have to answer to ourselves. Finally, let's talk about smart parts. A smart part not only fulfills a functional role, but it is also capable of measuring variables from the environment or from itself, such as strain, strength, pressure, or temperature. We can see that as a part to be measured and a sensor to be calibrated. In this example, we see a turbine blade which includes a thermometer. It has to have the correct external and perhaps internal geometry and deliver traceable temperature measurements. So, what are we doing as INTI? By now, we are printing parts from customer requests and for ourselves to gain experience as users. We are playing with the print parameters. Our printer has about 240 parameters on the setup, and each one of them has impact on the final result. We keep developing measurement and calibration capabilities, not only for additive manufacturing, of course. Up to now, clients don't bring any requirement or specification about accuracy or CMC. Most of them don't know what to expect about quality, and the most common specification is as good as possible. So we have a little time to understand the technology and develop expertise. There are 15 published ISO standards and 31 under discussion, so it is a matter of time until this becomes a requirement. On the other hand, we are researching. Additive manufacturing brings a lot of possibilities to change our world. We have to use it in order to save energy, materials, and natural resources and reduce waste. We want to have an active role on this, and that's why we are interested in develop a smart part with highly optimized geometries with active function like sensing and even acting. For now, we are at the study stage and we are managing some possibilities like glass fiber sensors, embedded strain gauge, and RFID chips, for example. Personally, I'm focusing my doctoral thesis in that direction, so I hope to be able to show progress in the medium term. Okay, that is all by now. I want to thank you for your kind attention. If you have any question, I will see you at the working group sessions.